Thank you, Eris, and good morning, everyone. Last evening at opening ceremonies, Louis Fauchon made the comment that water scarcity was built around, water security was built around three pillars: governance, finance, and knowledge. And what I'd like to do this morning, in my words, is focus on that third pillar, the knowledge one, and in particular focus on two elements of that knowledge base: data and the interpretation we make of those data. And these are issues that we within WMO's Commission for Hydrology expend a lot of our time and energy. Okay. Water arguably is the most consequential of all the potential results, impacts of climate change. Why? Well, because the effects on agriculture, the effects on aquatic ecosystems, energy, industry are largely driven by effects on water. And this community knows it, so I don't have to reiterate it here. It's really critical in terms of understanding the issue that we understand the changes in the quantity, quality, distribution of, and including the demand for water in response to climate. And though modeling is important, and none of us would discount that value of modeling, particularly with respect to understanding the potential for future impacts, the measuring and the describing of changes in water currently underway is of no less importance and certainly no less value. And it's an area that we have not emphasized as much as we really need to be doing. It's become common over the last 4 or 5 years at conferences, and particularly water conferences, you'll hear this message: you can't manage what you don't measure. And where does that come from? Well, Ralph Keeling, the son of Charles David Keeling, who started the CO2 monitoring network at Mauna Loa, said in a paper in Science a decade ago that the only way to figure out what is happening to our planet is to measure it. And this means tracking changes decade after decade and poring over the records. Now, there are 3 key ideas embedded within Keeling's quote. The first is understanding requires measurements. And while models are tools for learning and for testing at that understanding, they are not substitutes for observations. Secondly, measurement must occur over decades. Trends in short records, periodic oscillations in short record area of climate change, they've given no consideration to at all. And we need to be thinking about this, particularly for planning purposes. And I just added on this the note that what we deal with here is a characteristic in these long records, these long geophysical records, of what we refer to as long-term persistence. Second question in the water budget is, have changes occurred in the relation of annual or seasonal discharge to annual or seasonal precipitation? It's curious that in some studies that have been done, even though we're constantly seemingly of the sense that changes in climate are going to really drive changes in extreme, for the periods of record that we have available, the last 30, 60 to 70 years, and we've done sensitivity studies, the sensitivity of mean flow to mean precip, the sensitivity of peak flow to precip. What we've actually seen in a number of studies have been that mean flow seems to be much more sensitive to precip changes than peak flows. That raises all kinds of questions with respect to potential changes in opportunities as we move forward if precip is increasing, or potential challenges that we're going to have to face and deal with if we're dealing with decreases. So those are some important questions that have to be dealt with. Seasonal stream flow. And seasonal flows are particularly important in areas where you have snowmelt-driven stream flow regimes. Not exclusively, but that is a big highlight area. And so the question becomes, are the shifts that are currently taking place important to water management? That is, with respect to water supply, flood mitigation, aquatic ecosystem integrity. And if they're not, why aren't they? And how long would a shift have to continue before it becomes important to these kinds of issues? Again, an important consideration. Secondly, although climate change has been implicated as a likely case as a cause for the observed hydrologic changes that have been observed in recent years, to what extent could multi-decadal climatic oceanic oscillations or changes in groundwater development or in water use be responsible for these observed changes? If we turn to low flow, is there a pattern of change in the 1, 7, 14, or 28-day low flow pattern? You have to look at all of these things to find the subtleties in what is actually occurring, and you need the data sets to be able to do that. Are we seeing an unexpected number of new record low flows, more or less than what you would expect due to chance? In some places of the world, the answer may be yes. In other places of the world, maybe not. And to answer the question definitively, we have to have the data sets to do it. If low flows are changing, what are the relative influences of changing water use, groundwater depiction, reservoir storage, or intrabasin transfers on low flows? And some of these issues were addressed in previous comments that were made. And to what extent is it possible to predict regional low flows seasonally and annually based on North Atlantic and North Pacific sea surface temperatures, as hypothesized by some and as commented on earlier today? And in this regard, I would just draw everyone's attention to a study that was done more than a decade ago that actually looked at drought frequency during the 20th century, and it was done particularly just for the U.S. And it looked at both the Pacific decadal oscillation and the Atlantic multi-decadal oscillation. And in the upper left-hand corner of the screen, you can see a phase when the Pacific was warm, the Atlantic was cold. And in the lower left-hand case, you see the Pacific being cold and the Atlantic cold. What's important to note is when the Atlantic was cold, regardless of what the Pacific was doing, there seemed to be moister conditions across the conterminous United States. In fact, in some cases, it could have been 30 to 50% of the time when this configuration of the two oceans occurred that we found these patterns. And then similarly, on the right-hand two illustrations, the top one has a positive or a warm Pacific PDO and a warm Atlantic. And the bottom one, it's a cold Pacific and a warm Atlantic. Again, interestingly, it was the Atlantic that in its warm stage, regardless of what the Pacific was doing, seemed to drive these drier phases that we've observed in U.S. drought patterns. So these, are the kinds of questions that you want to be able to answer, but you have to have the data to do it. And finally, getting to flood and high flow characteristics. Many of the questions are similar to those in drought, maybe slightly different. Is there a pattern of change in the annual peak flow or in flood volumes? Because you do have to consider both. Is there a change in the timing of annual peak discharges? And this is particularly of concern in areas where you have water supply systems that are snowmelt driven. Is there a change in the number of the largest floods as defined by exceedances of some particularly high threshold? Are there any unexpected number of new record peaks, either more or less than would be expected by chance? And in a number of studies that have been done within the hydrological community, what we're seeing is no change in the frequency of peak flows. Some studies have highlighted the fact that there appears to be more water in some of these events than there was in the past, but not so much so that it was changing the frequency. And so To do the proper frequency analysis, you have to have the data records. Can the role that dams play in changing high flow characteristics be quantified? Dams are really an important issue, and in this particular context, they become even more important because in many parts of the world, local communities are looking to remove dams that were built for various purposes. Well, there are consequences of doing that, and you have to have the data sets to really understand before you make these decisions. And can any observed changes in peak flows be related unambiguously to changes in climatic factors and or land use factors? We already know that land use change has had significant impacts on the flow regime and on the peak flow regimes, particularly in areas that are affected by extensive urbanization. So these, again, are questions that we consider to be fairly important. My takeaway message here, and I'm saying this from WMO's commission from hydrology standpoint, because this is where we're putting an awful lot of our attention right now. The keys to understanding the role of climatic variability and change on water resources and aquatic ecosystems is ensuring the ability to monitor a wide range of hydrologic systems, particularly those already having long records and limited influence of man on the landscape. And within the Commission, our programs are aimed at helping National Hydrological Services build the capacity and sustain the records to be able to do this very thing. And secondly, to establish the capacity to substantially increase efforts to analyze existing records, to understand changes that are occurring, and to differentiate the relations of water resources to climatic variation, climatic change, and other direct human impacts on the landscape. What we're trying to do right now within the Commission is build a system for essentially monitoring the status and even go so far as to generate an outlook. And to do this in partnership with our national hydrological services around the world, particularly those in the developing world where the basis of records has just not been substantial enough to be able to address these questions. And with that, I think I'll stop, Eris. Thank you.